Dear students, today through this video we are going to get familiarized with the concept of unit load method, a very effective method when you want to analyze a determinate structure. That means if you want to calculate the displacements, that is the deflection or slope of any determinate structure, this unit load method approach is the very effective tool. So that's what we are going to see here. Unit load method. So we are going to start with the cases of beam. Okay, so when beams are subjected to bending moment, that is beam subjected to flexural load, we have the expression for strain energy as integral m square dx by 2ei. Similarly, we have the expression for deflection, that is delta, is given by integral mm dx by ei, where m represents the expression for bending moment, expression for bending moment due to external load. Capital M represents the expression for bending moment due to external load, and small m represents expression for bending moment due to unit load. And we are the one who will decide where the unit load should be applied and in which direction, and the type of unit load, because depending on the unit load, type of unit load, the result what we will be extracting from the same equation are different. If the unit load what we are considering is a load like having 1 kilonewton, a force, then we are going to get deflection in the direction of the unit load. If we are considering a unit load as 1 kilonewton meter moment, we are going to get a rotation. So we need to get a clear picture about the type of unit load we are going to apply. So the unit load there are two types of unit load we will be applying in these cases. So one is a load like this, having a force like this, having a magnitude 1 kilonewton. The second one is a moment having magnitude 1 kilonewton meter. Okay, so depending upon the load applied, if we are applying a load like this, what we are going to get is a deflection. Deflection are represented either by delta or by y. These are the different notations for representing deflection. The deflection what we'll be getting will be having two particular parameters or characteristics. One is the magnitude. You'll be getting the magnitude. The second is the direction, and the direction of displacement, direction will be in the direction of applied load. So if you are applying this 1 kilonewton downward, the result what we'll be getting will be a downward displacement. If you are applying this 1 kilonewton upward, the result what we'll be getting will be a displacement in the upward direction. And when we think about applying 1 kilonewton meter moment as the unit load, the result what we'll be getting will be the rotation at that point. And that rotation also has got two parameters. One is the magnitude, the other one is direction. And here, whichever direction we are applying the point load, that is, if we are applying the point load like this, this will give a rotation in the clockwise direction. If you are applying a load like this, the result will also be a anti-clockwise or counterclockwise direction slope. So these are the basic things that we need to remember when we are using unit load. So the expression we are already having, delta equal to integral mm dx by ei. Ei is the flexural rigidity. Capital M is the expression due to external moment, bending moment expression due to external load. Small m is due to the unit load, and the unit loads are classified like this. You can either apply a force having 1 kilonewton magnitude, or you can apply a moment having 1 kilonewton meter. If you are applying a force, you are going to get a vertical deflection. If you are applying a moment, you will be getting the rotation. And the direction of the application of the load decides what is the direction of the result obtained. Okay, so this is the basic introduction what you need to have before using the unit load method. So we are going to start with a very simple example where we are going to talk about a cantilever subjected to a point load at the free end. Okay, and we are considering the parameters, physical parameters as L and EI, and E is the material parameter, and we are assuming that the flexural rigidity is constant throughout the length. Now we want to calculate the expression for say y. I'm giving some names, say let this be point A and this be point B. I want to get the deflection at B, the vertical deflection at B, and rotation at the point B. These are the two parameters that I require. Okay, and when you see this, okay, when we have a system like this fixed at one end and I'm applying a force, it bends. Okay, when it is bending, okay, I can plot the displaced profile. The displaced profile will be something like this. Now I want to know what are these two parameters. In the image, what are these two? So YB is basically this distance. This is what we call as YB. And what is theta B? Theta B has got a particular way of representation. So when you want to calculate the rotation at a point, say if I want point P, so what I will do is I will just extend this. Okay, and at point B I will be drawing a line parallel to the original beam. Okay, at point B, okay, this is a point B. At the point B I will be drawing a line parallel to the original beam, and the direction of rotation is from the line that we have drawn to the displaced profile. Okay, I will give an enlarged view. So this is what our original beam is, and let this be our displaced profile. And if I want to know the rotation at this particular point, I will drop a line like this, and I will draw a line parallel to the original beam, and this direction, okay, direction from the newly drawn line to the displaced profile, this is the direction of rotation. So in this case, if I'm calling this point as say point B, the rotation at point B is theta B in the clockwise direction. Okay, we need to have a clear picture how to get the direction of rotation from the displaced profile. So this is what we do. Draw a parallel line to the original beam, get the direction from the parallel line to the displaced profile. So here theta B is clockwise, and we know that the deflection is downward. So we can assume these two things by plotting the displaced profile. Now we are going to see how to calculate it. So we have the directions, but we don't know the magnitudes, and even we are not sure if it's a combination of load. It's a simple load, so we can predict the shape. If it is there are like 3 or 4 or 5 villains acting together, that is 4 or 5 loads are acting together, we may not be able to plot the displaced profile this easily. In such a case, we may have to go for the calculation part. So here also we want to get the magnitude, so we are moving into the calculation. Okay, so we are going to think about this problem in the problem aspect. So we want to calculate delta, okay, mm dx by ei. So there are different things. M is there, okay. So I need separate figures for calculating this. So first I'm going to calculate the YB part, okay, that is the vertical deflection at B. For calculating any deflection or displacement, you need two figures. One is the M figure and the next one is the small m figure. Okay, from this M figure we will be fetching the data for capital M, small m will be fetching the data for small m. Okay, so what are these two figures? So we have this beam. Okay, so I'm going to represent it as the reactions. Okay, LEI. Fine. So whatever the given figure is, that itself can be used for the capital M, because we are dealing with the beam and the external load. So the external load is given in the problem. So plot the beam with the external load and that forms the M figure. So the given beam itself is the M figure. Now when we are going for the small m figure, that is the one which we need to be very careful. So here we need to decide what type of unit load need to be applied and in what direction. Okay. So here I'm plotting the beam. So this is the beam that is given in the problem without any load. Okay, I just use the beam without the external load. So I'm having a cantilever beam. So the reactions are going to be like this. And now I want to apply the unit load. So the unit load need to be applied at the point where I need the displacement. I need the displacement or deflection at point B. What I want is the vertical deflection. So I need to apply a unit force. Okay, so the unit force need to be applied at point B. Okay, need to be applied at point B, and the vertical deflection is what we wanted. So I am applying the unit load like this. Okay, the unit load is applied at point B, and as we want the deflection, it's a point load like this. So if you are able to plot these two diagrams, then half the part of the problem is over. Okay, now what we have is the calculation part. Fine, so we have this. Now we are going for the tables that we have seen earlier, moles table. Okay, so the same table we are going to plot. Okay, so S, E, okay, L, O, M. When we are using unit load method, I will be having an additional M here, that is a small m. Okay, now I can have a table. So fine. Now I want to see how many segments are there. So how to separate a beam into segments, we have earlier in the earlier lectures we have discussed. So we are going to use that concept here. So how many segments are required here? So to decide that, you need to look both your capital M figure and small m figure. Okay, so whichever is having higher number of segments, that should be used in both cases. Okay, here it is pretty simple. When there are multiple loads and multiple points, then we may have to think about that. So we'll start with this and we'll see the rest of the case later. So here you can see segment, just this is the location of one point load, location of one point load, so segment 1. Location of point load, location of point load, segment 1. So just one segment is more than enough in this pretty case. So segment 1. Now elasticity, flexural rigidity, it is EI in both cases. Limit, the limit is 0 to L. Now I need to decide where the origin should be. We have earlier discussed, whenever you're using a cantilever beam, the free end is the best option. So I'm choosing B as the origin. Now I want to get the expression for capital M and small m. To get the expressions for capital M and small m, take is random section, okay, XX, at a distance of X from the origin. Okay, this also we have seen earlier. But here you should be very careful. You should be using the same section in both capital M figure and small m figure. This section should not change. Consider the same section, consider the same X. Okay, because here we are going to put the same X and we are going to integrate with dx. So you should be very careful with this part. Now we are going to calculate the values. So m we will get from here, small m we will get from here. So I want moment at this point. So what will be the magnitude of moment at this point? If I'm looking to the right, P times x. P is the force, x is the lever arm. So I'm going to get Px as the magnitude. What about the direction? To get the direction, fix the point, apply the load. This is hogging shape, hence it is minus. Now I'm checking here. I need moment here. So what will be the moment? 1 into x. So magnitude is x. Now I need to check the direction. So direction is hogging. So it is minus. Okay. So once you have this table, now it's just the integration. Okay. So we have the expression delta equal to integral mm dx by EI. So here what we are talking is YB. So I'm putting it as YB equal to integral m into m. That is minus px into minus x, which is px square dx by EI within the limit 0 to L. So once I integrate this, I'm taking the constants out. So P by EI comes out. Okay. Then x square dx. Integral x square dx is x cubed by 3 in the limit 0 to L. So I'm going to get x cubed by 3 in the limit 0 to L, which will give me PL cubed by 3 EI, which is the vertical deflection at the free end for a cantilever acted upon by a point load at the free end. Okay, so you need to go it step by step, and in the first few problems you may feel it as a cumbersome process, but as you do or practice, this is a very simple process, and you know it or not, those people who are doing integration, we are having different methods to calculate displacement. This is one of those methods. Okay, and you should know that the people who normally do this integration and differentiation are considered to be genius, right? We also know that we are seeing some integration, we will get afraid. So most of the people are like that only. So if you're using these integrals to solve something, then people will think that you're a genius. So it's a shortcut method to feel or look like a genius. So this is part 1 where we calculated the vertical deflection at point B. Now let's see how to calculate the slope at the same point B for the same figure. Okay, so let's try that now. So I'm keeping the paper apart and I'm taking the new paper, and I'm just plotting the beam again so that we won't have to refer back to the old paper. So this was the case. This is point A, this is point B. Okay, now we have the expression delta equal to integral mm dx by EI. Now here we want to calculate theta B, rotation at the point B. So if you want to get rotation, the unit load that we want to apply is a moment having magnitude 1 kilonewton meter. Fine. So let's go step by step. So whenever we get such a problem in unit load, we'll be drawing the capital M figure, small m figure. Capital M figure we earlier we discussed, it should be the same figure as given in the problem, and the small m figure should be the beam with the unit load. And in this case, the unit load is 1 kilonewton meter moment, and that need to be applied at the point where we want the displacement to be calculated. So we want to calculate the rotation at the free end, so it should be applied here. Okay, so on application of this, we are going to get that. Fine. Now let's see. Now after getting this, we'll be going for the regular case, that is SELOM, and as it is unit load method, small m. Okay. Now how many segments are required? So you can see here one segment, here also one segment, and I'm taking a common section that cuts both the cases at a distance of x, at a distance of x. Now, so there is one segment. Okay, so segment 1, EI is constant, limit is 0 to L. As is a cantilever B, I'm taking B as the origin. So what is the expression for bending moment? Here the expression for bending moment is Px. Okay, and it is sagging or hogging. Are you able to predict it? We have been practicing it a lot, still we'll try again. So apply the load, it's hogging, so it is minus. Now I'm taking this case, so I want the moment here, the small m value. So the lever arm doesn't matter when it is a moment, so what I have, the magnitude is 1. What about the direction? Okay, to assume the direction also we can use the same technique. So this is a beam. Okay, I'm fixing at this point, and at the free end I'm applying a moment in this direction. A moment in this direction creates a hogging moment, which means it is -1. Now I can substitute the different values I got in this equation. So theta b, because that's what the displacement we are calculating, integral minus px mm, so minus px into -1, which is basically px dx by ei within the limit 0 to L, that is, I'm taking the constants out, so p by ei, integral x dx is x squared by 2 within the limit 0 to L. So this is going to give me the value of theta b as P L square by 2EI, which is the magnitude of the rotation. And what about the direction? Okay, the direction of rotation will be same as the direction we assumed for the unit load. The unit load we assumed as clockwise, so the rotation what we finally get is also in the clockwise direction. Okay, so we got the rotation at the free end as PL square by 2EI clockwise, and in the previous calculation we got the deflection as PL cube by 3EI. Here we didn't put this direction. What will be the direction here? The direction of the assumed unit load. The unit load was assumed downward, so this deflection what we got is downward. Now we can refer back to the graphical approach that we performed by assuming the deflected profile. In the assumed deflected profile, we can see that the deflection was downward, the rotation was clockwise. Here also we got the deflection downward and rotation we got it as clockwise. So this is how we apply unit load method for the calculation of displacements, that is slope and deflections. Okay, so this is a very basic problem. Okay, so in the next further videos we will discuss about other problems, or else this video is going to be too long. Okay.